One of the most common uses for the conservation of momentum is when dealing with collisions. When we talk about collisions, there's some certain rules we have to understand. That when we talk about the items involved in collisions, these items together make up the system. So now if we have a closed system, meaning we're taking account all the items involved in the collision, if, the beginning and the end. If we have a closed system, that the total change in momentum, should be zero. That means the total momentum you started off with has to equal the total momentum you end with. So if two objects have a total momentum of 20 kilograms meters per second, then at the end they have to have a total momentum of 20 kilograms meters per second, which we saw in some of the problems we did in the last example. Now, when we talk about collisions, there's mainly three types of collisions. One of the types of collisions is called an elastic collision. Now, for the elastic collision, there's certain rules. An example of an elastic collision is, imagine we have two objects moving towards each other. They're going to collide. One has a mass and the other one has a different mass, but they're both moving towards each other. Or they're going to collide. Maybe they're moving away from each other, but one's moving faster. But either way, when they collide, it's considered an elastic collision if they pretty much end up moving after the collision. So when two objects collide and continue moving is a type of elastic collision, but it's a little bit more specific than that. Specifically, one of the main rules for an elastic collision is that the kinetic energy has to be conserved, meaning the total kinetic energy you started off with is equal to the total kinetic energy you ended with. So if two objects collide and the total kinetic energy doesn't change, it's considered an elastic collision. Now, really, normally when we look at the macroscopic, which is like from the big picture, we see objects colliding, there is never a real elastic collision. You're always going to lose energy because when two objects collide, there's going to be heat, or it's going to create sound, or the object's going to get deformed. All this involves energy. So the total kinetic energy is never going to be completely 100% conserved when two objects collide. But we can still consider an object elastic if the change in kinetic energy is very, very small. We can say it as being negligible, and we can treat it like an elastic collision. So when you play pool, the pool balls are made in a certain way that they are treated as an elastic collision. So that's a very common example of a real-world elastic collision. So again, elastic collision pretty much means two objects collide and their change in kinetic energy is equal to zero, and their total change in momentum is also equal to zero. But then remember, the total change in momentum equal to zero is true for all collisions. So what happens when two objects collide and their kinetic energy changes? Well, then it's considered to be inelastic. Now, there's two types of inelastic collisions. There's perfectly inelastic collisions, and they're just simply inelastic collisions. Perfectly inelastic collision is when we have two objects that collide just like before, but instead of moving separately as they were in the beginning, they collide and form one large object that ends up moving in some kind of direction. So perfectly inelastic collisions involves two objects colliding, combining, and becoming one giant object. Inelastic collision is just two objects collide and they end up moving and they don't become one object. They just end up moving in some kind of direction. Very similar to an elastic collision, but again, in an inelastic collision, there is a change in kinetic energy. Now, keep in mind, for both elastic, inelastic, or perfectly inelastic, if you take into account both or all the objects that are colliding, the total change in momentum has to equal zero, meaning the momentum you started off with has to equal the total momentum you end with. This is true for any type of collision. Now, what happens to the kinetic energy can vary depending on the collision. So now we'll go on and look at some examples. Alright, for our first example, we have a problem that we have. It tells us that Batman has a mass of 91 kilograms and he jumps straight down from a bridge into a boat with a mass of 510 kilograms, in which a criminal is fleeing. The velocity of the boat is initially positive 11 meters per second. What is the velocity of the boat after Batman lands on it? So we have this situation where we have Batman, he's jumping off a bridge, and he has a mass of 901 kilograms, and he's coming down and about to land on a boat that is moving forward along the water at 11 meters per second. And they want us to know what happens, what is the velocity of the boat after Batman lands on it. So we're trying to find the final velocity of the boat. So the collision is perfectly inelastic. It's perfectly inelastic because when Batman lands on the boat, they're going to pretty much become one object, right? Batman moves forward, the boat's pretty much moving forward. So we treat it as a perfectly inelastic collision. So kinetic energy is going to change. But even though kinetic energy is not going to change because it's still a collision, the total change in momentum has to equal 0. So the total momentum at the beginning is equal to the total momentum at the end. And because momentum is a vector, we can treat it as the total change of momentum in the x direction has to equal the total change of momentum in the y direction. But the main thing we're going to be concerned with is the total change in momentum in the x. Total change in momentum in the y is really, really weird because even though when Batman lands on the boat, technically the boat should start moving downwards with the same momentum it started with, but because the water's there to kind of like balance it out, the boat's not going to sink. So if we assume that the boat doesn't sink, we can ignore what is happening with the total change in momentum in the y. So if we just focus in on the x, we first look at what is the initial momentum in the x of this collision. So the total initial momentum in the x is equal to the mass times the velocity of Batman in the x plus the mass times velocity of the boat in the x. So we're taking into account the two items we're looking at. Now, the total momentum in the x of Batman is going to be 0 because he's not moving in the x direction, he's only moving in the y direction. And the momentum of the boat in the x direction is just 510 times 11. So the total momentum in the total initial momentum in the x is simply going to be 5,610 kilograms meters per second, which means that the total momentum in the x at the end has to also equal 5,610 kilograms meters per second. So when we add up the mass of the boat and Batman, because when Batman lands on the boat, they're going to be together, they're going to be treated as one thing. So when we find their combined mass and multiply times our unknown velocity, they should equal 5,610, meaning that the final velocity of the boat with Batman in it should be 9.33 meters per second. Now this is less than the boat's initial, which makes sense, right? The boat's moving at 11 meters per second. Suddenly the boat is heavier, so it's obviously going to slow down a little when Batman lands on it. So the final speed of the boat is 9.33 meters per second. The next problem is a very common problem. We have a projectile that has a mass of 0.20 kilograms and is fired at an and it embeds itself into a stationary target with a mass of 2.5 kilograms. And it says, with what percentage of the projectile's incident kinetic energy does the target with the projectile in it fly off after being struck? Alright, so basically we have like a projectile. Let's say it's a bullet. And it's going to move forward and collide with another object. After they collide, the bullet is going to become embedded inside the object, meaning this is a perfectly inelastic collision, meaning there's going to be some kind of change in kinetic energy. And the problem is asking us is what is the percentage of the projectile's kinetic energy what was the percent change of the object's kinetic energy. So we don't know how much of the kinetic energy was lost or gained. I can tell you right now it's going to be lost because when something collides into another object, there's heat, there's deformation, so some of that kinetic energy is being converted into another. So we're trying to see how much kinetic energy is lost. So we need to look at it in a couple of different ways. What is the change in the kinetic energy? What is the percent change in the kinetic energy? Well, the total kinetic energy initial is equal to the kinetic energy of the bullet and the kinetic energy of the block. Now, so we don't know what the velocity of the bullet is. We do know that the initial kinetic energy of the block is 0 because the block isn't moving. So our total initial kinetic energy is just 1/2 times 0.2 times its initial velocity. So when we kind of clean it up a little bit, it's our total initial kinetic energy is 0.1 times the initial velocity of the bullet squared. And our final kinetic energy is equal to 1/2 the mass of the block and the bullet because they're embedded together, which is where we got that 2.7 kilograms. The block had a mass of 2.5, the bullet had a mass of 0.2. So the kinetic energy is 1/2 times 2.7 times Vf squared. So we can clean it up and say that the final kinetic energy is 1.35 Vf squared. Now, again, we're doing a lot of problems. We're doing a lot of different formulas. There's a bunch of different ways you can solve this. So you can solve this problem in a different way than I do, but at the end we should ideally get the same answer. So when we're trying to compare the initial kinetic energy and the final kinetic energy, we can use the systems of equations so that we can have a common variable. Right now we have the initial kinetic energy in terms of the initial velocity and the final kinetic energy in terms of the final velocity. So we want to come up with an equation that kind of combines them so we can compare how their numbers are going to relate. So we can use our conservation of momentum equation to compare our total initial momentum to our total final momentum. Then we find out that the relationship between the final velocity and the initial velocity is that the final velocity is 0.2 over 2.7 times the initial velocity. So the final velocity is going to be much less than the initial velocity. And then we can use a system of equations to kind of plug that back in. We can find out that the V final squared is equal to 4 over 1,458 V initial squared. So basically we can rewrite what the kinetic energy final is in terms of the initial velocity and then compare it to the initial kinetic energy. And when we're trying to find the percent change of something equals the amount that it actually changed divided by the initial amount. So when we divide the difference of it, so the kinetic energy final is 4% of the original kinetic energy. Meaning when we take our kinetic energy initial and divide it by our kinetic energy final, the two VI squares cancel out and we get about 0.04. That means 4% of the original kinetic energy is still existed, or let me rephrase that. The final kinetic energy is 4% that of the initial kinetic energy, which means that there was 96% of the total kinetic energy you started off with was lost during that collision. 96% of the energy was converted into something else because of the possible heat or deformation. And that would give us our answer, which is with what percentage of the projectile's incident kinetic energy does the target with the projectile in it fly off after being struck? It lost 96% of its kinetic energy. Okay. For our last example, we have the following problem. This is number 39. We have a girl and she is skipping stones across the lake. One of the stones accidentally ricochets, meaning it hits and bounces off a toy boat that is initially at rest, meaning the initial velocity of the boat was 0. In the water, see the drawing. The 0.072 kilogram stone strikes the boat at a velocity of 13 meters per second, 15 degrees below the due east, which is shown in the picture, and ricochets off at a velocity of 11 meters per second, 12 degrees above due east, also shown by the picture. After being struck, got a little ahead. After being struck by the stone, the boat's velocity is 2.1 meters per second due east, and it's asking what is the mass of the boat, and assume the water offers no resistance to the boat's motion. So let's look at all our initial values. So we know the information of the stone, we know the mass of the stone, we know the initial velocity and angle of the stone. So using that in our trig, we can find the stone's initial velocity in the x, which is 13 cosine of 15. And the initial velocity in the y, which is negative 13 sine of 15. Now I put negative because if you look at the stone, it's moving in the negative y direction in the beginning. Now if we look at the boat, we don't know the mass of the boat, but we do know it's at rest in the beginning. So the initial velocity in the x and the initial velocity in the y are both 0. So we can calculate the total initial momentum in the x by taking the mass and initial velocity of the stone and adding it to the mass times initial velocity of the boat in the x direction, which is going to be 0 because it doesn't matter what the boat's mass is, it's at rest. So its total momentum initially in the x direction is 0. So our total initial momentum in the x is simply 0.904 kilograms times meters per second, which also tells us that the final momentum in the x should also equal 0.904 kilograms times meters per second. So if we look at what's going on at the final value or at the end, we have the stone's mass, we have the stone's initial velocity, we have the stone's final velocity, that's a typo. So they give us the final velocity and they give us the angle. So using trig, we can find that the final velocity in the x of the stone is 10.76 and the final velocity of the stone in the y direction is 2.29 meters per second. We still don't know the mass of the boat, but we do know that the final velocity of the boat in the x direction is 2.1 meters per second. That was given to us in the problem. So we can calculate the final total momentum in the x by taking the momentum of the stone in the x direction and adding it to the momentum of the boat in the x direction. Now, we don't know the mass, but we do know velocity. And we do know that the final total momentum in the x should be the same as the total initial momentum, which was 0.904. So plugging that in the value, we can calculate that the mass of the boat must have been 0.06 kilograms, which gives us our answer. So the mass of the boat was around 0.06 kilograms. And then we have our final answer.